Yes, viewers. Hello, viewers. My name is Robert Bolaños, and this is my presentation for the FDTD domain simulation and analysis for the 1D, 2D, and 3D. To kind of give you guys a little bit of an idea of what to experience within this presentation, within this PowerPoint, as well as all the other PowerPoints, this is my table of contents for the first one. And this one, and every time there's a table of contents, these will highlight the specific topics that will be covered in every PowerPoint slide. So the goal was to simulate a 1D FDTD problem by first applying a PEC, which is known as a perfectly electric conductor, without using the absorbing boundary conditions. Then we had to simulate the 1D FDTD problem again by using the ABC. The FDTD problem that was assigned is to simulate and calculate the electric and magnetic field values somewhere inside a square structure by using a certain current source. The first simulation was designed to use a PEC as the boundary conditions and neglecting the ABCs. This implies that the domain has to be large enough so that when the waves hit the boundary, they do not have enough time to come back at a certain point. The second simulation will use the ABCs as the boundary conditions. This implies that the domain would be smaller, which would result in the same resolution. So the finite difference time domain, also known as the FDTD, is a technique that is gaining popularity in computational electromagnetics over the past decade based on the fact that it is straightforward and is efficient during analysis work. This technique has been used in various applications such as scattering from metal objects. It is also used for antennas because a single FDTD simulation with a pulse source, which means that the source is an AC, can be used to determine a frequency response of any kind of antennas. Specifically, it is basically used for broadband antennas. The FDTD is also used for microstrip circuits because any type of circuitry involves a lot of high frequency, and the FDTD method is very versatile with high frequency circuits, meaning that it is very versatile and it is capable of dealing with any kind of high frequency circuits at all times. And it's also used for absorption because the FDTD method has been used in calculating the scattering of metallic objects as well as calculating the interaction of EM fields with complex and lossy dielectric bodies. In this 1D FDTD problem, the biggest factor is that the FDTD can be used to implement a general solution of Maxwell's equations. In order to do that, a computational domain must be defined first. The computational domain is defined as the areas as to where the simulation will be performed. This is where dimensions become vital when it comes to simulating. Then at every point in space, the electric and magnetic fields have to be determined within that computational domain, as well as the material that will be used within each cell. The material can be defined as either free space, which is also meaning that it's air. It can be metal or dielectric. Basically, it can be any material as long as the permeability, permittivity, and conductivity are specified. Then once the computational domain and the grid materials are established, then the next step is to determine the source. Now this source can be either a current flowing down a wire, you can have an electric field, you can also have an impinging plane wave, you can also have a sinusoidal source, there's also a Gaussian source, you can also have an impulse, any other source right here depending on the design of the project or the problem itself. The output of the simulation is usually either the electric or magnetic fields at a point or a series of points within that computational domain. Now when it comes to simulations, there can become issues in computing the fields at the edge of the FDTD grid. The reason behind that is the absorbing waves can cause reflections at the edge of the grid, which will contaminate the fields that are located inside the grid. Based on the simulation, there has to be a special kind of boundary condition that has to be applied in order for the field components to keep going and preventing the field components from being reflected back into space. The answer to that solution is the use of absorbing boundary conditions. These boundary conditions are commonly used for problems where the modeled computational domain is extended to infinity. These boundaries are located on the outer part of the grid, which is the area that allows all the waves to exit with no possibility of any reflections. In one-dimensional cases, the required boundary conditions are simple and exact because there will be plane waves that are normally incident on the edges of the grid. However, for 2 and 3-dimensional cases, the problem becomes more difficult because the plane may not be planar. Well, the setup of it as far as the coding was really not that complex, so there's really not a lot as far as explaining or kind of demonstrating anything as far as code goes, but pretty much the output is what you see here as far as my grid is concerned. And basically, the setup is basically a sinusoidal wave that's hitting a lossy medium that has a dielectric constant of about 4 and a conductivity of 0.04, where the EX model is modeled within the code itself. Lessons that I've learned within this within the 1D FDTD problem is that the analysis to me is like fairly simple, when the reason why it makes it very simple is because of how Maxwell equation and also the FDTD, how they're connected because of the fact of how the analysis just works. I mean, I pretty much when I first started, I had no idea how was this going to be working out, whether I had to do some kind of complex or advanced math. But in reality, once I was able to find out the connection between those, it just kind of makes the analysis flow. And knowing that it's 1D, it makes it a lot more easier as far as how to calculate the fields and so on. However, the one thing I would have to say, the hardest part of the simulation is determining whether or not the absorbing boundary conditions were going to be inserted, because as mentioned in the goal was you had to basically insert them without it, or you basically had to insert without. You basically had, because the goal of the project was pretty much to determine whether you had to use them or not. If you do use them, then you can neglect the PEC. Otherwise, you have to use the PEC, and therefore it was kind of tough to understand about when can I use them though here, and when can I use them in the code right here, knowing that it's kind of tough to kind of implement them in and whether to implement PEC. And then also determining the cell size was also a big issue, because the thing is, the cell size, it depends. It can be whatever. It can be whatever depending on the problem is stated though here. Otherwise, it's important that the cell sizes are pretty much exact, because you always want to have the right results as far as like the accuracy goes. So it made a lot more trial and error as far as trying to figure out what kind of cell size do I needed to get for this particular problem. Okay, moving along here, we also have, this is for the 2D FDTD domain simulation analysis, and this one is also applying a really known, this one is also applying distinct boundary conditions known as the PML. As mentioned though here, this is my table of contents here for this one. Now this one would be a little bit different though here, depending on the certain type of topics that you see here. So pretty much the goal for the second one is that I had to complete a 2D FDTD problem by simulating a TE and TM modes separately. For each mode, I'm supposed to add the PML boundary conditions for each separate modes. So the main question before diving into the design approach and anything like that is, what is a PML and what is it used for? Well, basically, these conditions are used for wave equations that are commonly used to shorten computational regions in order to simulate problems with open boundaries, especially with the finite difference time domain method. The key difference that distinguishes these kinds of boundary conditions to any others is the design and purpose. And the reason why I say this is because when a wave from a non-PML source hits the boundary of a PML, the wave will not be able to bounce back towards the interface. This allows the PML to become stronger when it comes to absorbing boundary waves. This allows the PML to become stronger when it comes to absorbing boundary waves from the interior of a computational region without having the waves bouncing back. The PML is constructed in which there is no loss in the direction of the interface. There are two conditions in order to form a PML. The following conditions are: first, the impedance going from the background medium to the PML must must be constant. Therefore, the impedance has to equal to 1. Second, the direction that is going perpendicular to the boundary has to have a dielectric and permeability in other directions, meaning that it has to be inverse to those other directions. So the transverse electric waves are waves where the electric field is everywhere as long as the field is perpendicular to the direction of propagation. These waves focuses on the H fields and are defined when EZ is equal to 0 while HZ is not equal to 0. The transverse electric waves, or TE waves for short, are mentioned because they are basically similar and operate under a certain mode called the transverse electric mode. In this mode, there will be no electric fields in the direction of propagation. They are called H modes because there is only magnetic field along the direction of propagation. Transverse waves, on the other hand, are waves where the magnetic field is everywhere as long as it is perpendicular to the direction of propagation. These waves focus on the E field and are defined when EZ is not equal to 0 and HZ is equal to 0. So it's basically reverse of what the TE waves was concerned. The transverse magnetic waves, or TM waves for short, are mentioned because they are basically similar and operate under a certain mode called the transverse magnetic mode. In this mode, there will be no magnetic fields in the direction of propagation. They are called the E modes because there's only electric field along the direction of propagation. For the design approach for the TM simulation, basically the results that I was able to produce as far as the design process goes is an 8-point PML with a sinusoidal source that operates at a point that offsets 5 cells from the center in both the X and Y directions. As the wave reaches the PML, the perfectly matched layers, which is 8 cells on every side, it becomes absorbed. As mentioned, once the PML starts to absorb the waves, that PML will become stronger every single time. By plotting the shape, it would remain circular. However, if the waves get within 8 points of the edge, which is inside the PML, then the shape will become distorted, and therefore it will not be circular anymore. Here is the result that I was talking to you about this 8-point PML with a sinusoidal source, which offsets the 5 cells from the center in both the X and the Y directions. So for the TE mode, or the simulation, the goal is to solve for Maxwell's equation for a TE wave in the XY plane having components of EY and EX and polarizing magnetic field HZ in the Z direction. The electric fields are defined at every half coordinate of space steps. This is where all the physical parameters of free space are equal to 1, which is part of the conditions to form a PML. The EX part is defined at every half Y coordinate and every full X coordinate, and the EY part is determined at every half X coordinate and full Y coordinate. The E and H fields are updated every full time step by using the difference form of Maxwell's curl equation. A perfect electric conductor is chosen as the source, which is located at the center of the domain. The type of source can be questionable depending on what the analyst is using. Other types of sources are sinusoidal, Gaussian, and impulse. The source is available in 4 standard forms, either unit time step, impulse, Gaussian, or sinusoidal forms. And as you can see, this is my TE simulation output results I was able to get. I was able to get, for this one though here, at a time step about 200. And you can see how the plots of this one here gets you can see that I'm able to get all the shapes as far as the circulars is what I was mentioning, and also I was able to do it for when applying it for the PMLs for the EZ. You can see how it kind of matches a little bit about what I was able to show for the TM, but only except this is only at a time step of about 400. So conclusions or lessons that I've learned is that now this is where the simulation gets a little bit tricky, because now you're starting to add in a lot about PMLs. As mentioned, you're able to now this is getting where the code starts to get a little bit more advanced, and this is where now you have to find out a lot more about how this is able to how the TE and the TMs, how they're basically work. So it can get a little bit tricky at times as far as how they're going to be able to work out. The importance of the PML boundary conditions, I found that to be very important, and I've gained a lot. I learned a lot about them as far as like what makes them so distinctive, and also what makes them unique. And the one thing I also learned about them was that many of you guys might question, well, basically, if you go back to the 1D FDTD, you were explaining about ABCs, so why can't you not apply ABCs into this particular slide? Like, why do you have, what makes the difference between PML and the ABCs? Which is a very good question, which I really thought about a lot. And pretty much what I found out is that the difference between the PML and the ABC is that the PML provides lower reflections by an order of magnitude. And also, as mentioned, the PML gets stronger by absorbing waves. Therefore, the PML uses an absorbing region rather than a certain boundary condition like the ABC. So to me, that's just pretty much the two difference between them, is that the PML provides lower reflections by an order of magnitude, and that the ABC is more of an absorbing region rather than just a simple boundary condition like the ABC. So that's kind of like the important things about what you're able, that is distinguishing between the PML and the ABCs. And some of the hardest parts of the simulation was basically the setup of how the PML boundary conditions was set up, because I kind of felt as though there was a lot more details about what had to be involved with the PMLs, and how is it here that it was basically set up as far as like the coding goes. So it took a little bit of time to try to figure out how is it that I was able to implement this, as well as trying to understand a little bit better about how could this go work out well. And the other part that was also hard was pretty much the dimensions, because I figured that the dimensions, just like the time step, it's very difficult, because you always gonna try to play around with the numbers just to see if you can get accurate results, or if you can actually find accurate graphs or measurements right here that are gonna support what you've done in certain simulations. So it's kind of hard. Plus, you kind of had to, it's a trial and error pretty much. So that's what makes it very hard as far as like trying to find the dimensions just to get the correct verification as far as the values go. So now we're going to move on to basically the 3D domain simulation. Once again, this is the table of contents though here for this particular slide or PowerPoint. So pretty much the goal for this one is that I'm basically going to implement a 3D FDTD problem and replicate the figures in slides 5 and 6. So pretty much a dipole antenna is one of the simplest and least expensive out of all types of antennas. They are mostly popular in radio communications. The dipole, out of all the classes of antennas, is the only antenna that is capable of producing a radiation pattern that can be similar to a simple electric dipole. The dipole antenna consists of two terminals or poles for the current to flow. This current and voltage causes electromagnetic or radio signals to be radiated. The antenna consists of a radiating element that is split, normally in the center, to allow applied power to be carried over to the transmitter. The length of the radiating elements determines the specific properties of the dipole antenna from its impedance, directivity, gain, beam width, operating frequency, and etc. The dipole antenna is the antenna that is used for its gain, which also implies that the antenna can be measured in free space. Therefore, for the simulation, the dipole antenna will be modeled for the first part of the simulation. As you can see, this is pretty much my output simulation graphs that I was able to form as far as two separate dipoles, two separate simulations. One will be the dipole into free space, which is the simulation or the output simulation that I had generated. And the other one is also the plane wave on a dielectric sphere. This one's going to be the more hardest one here because this one does require a dielectric sphere. But the other one that I just showed you, that's where the dipole antenna is going to be actually modeled as far as the simulation goes. So this is pretty much my output simulation here for this particular simulation. So the design approach for the dipole in free space simulation, this is basically a basic three-dimensional FDTD program with a source in the middle of the space. In this three-dimensional simulation, the electric field will start to decrease as the distance of the square propagates out from the point source. This makes it very difficult to see this effect in action. However, by using a dipole antenna as the source, this will allow me to see the electric field decrease when performing the simulation. Using the FDTD simulates a dipole by setting the GAZ parameters to 0 in the cells corresponding to a specific metal. This allows the EZ field at this point to remain at 0. The source is identified by setting the EZ field in the gap to a certain value. The output simulation gives me the propagation of the EZ from the dipole in the X and Y planes with the gap of the dipole in the middle. And as you can see, as I was mentioning about the GAZ, this is also an example of what I meant about how the GAZ is supposed to be set up. Specifically, when I'm specifying the dipole, you can actually see that what I had mentioned was that the GAZ parameters are set to 0 for the cells to be corresponding to a specific metal. You can see that once I've entered in the GAZ, it's actually set up equal to 0. So that's kind of an example of what I'm able to use here as far as how the GAZ works. One of the main setbacks that makes the transition from the main problem space to the PML is the parameter IDZ. This parameter is an additional three-dimensional array that is dimensioned throughout space. The three-dimensional procedure will have a total of 6 arrays, which will complicate the simulation. Therefore, the parameter IDZ will be broken into smaller three-dimensional arrays. Since the goal of the simulation is to generate a plane wave in 3 dimensions, the next step is to start putting objects in space to see how the plane interacts with them. As a result, the interaction of plane waves with a dielectric sphere can be determined throughout an expansion of Bessel's functions. These functions are defined by using the separation of the wave equation in both cylindrical, polar, and spherical coordinates. The parameter zdist, also known as zdist, calculates the distance at the point as if it were half a cell further in the z direction. The output simulation shows the electric field flowing out from the dipole source, which is set up by using a simulation that requires a 7-point PML. Parts of the field that is not associated with the PML radiates in a circular form from the source. The circular diagrams illustrate the fact that the fields remain circular until they reach the PML. So for this particular simulation, one of the things I've learned is that the simulation is now hard. I would have to say it is kind of hard now because pretty much I want to say that the first simulation was a little bit on the easier side, but this one took a lot more as far as trying to understand the code and trying to fit in a lot of this other stuff. Plus, I did mention though here that this one was going to be requiring. I believe that this one was going to be requiring a lot more. That this one was going to be a lot more complicated as far as having like 6 arrays. I believe is what I said. Oh yeah, 6 total arrays, which is going to really complicate the simulation. But it's really the only way here that you could have to do it. And so it was kind of hard to kind of set up the simulation and kind of set up the coding and stuff like that for it. The other thing is that I've learned a lot was about the dipole antenna and how it's basically used for the FDTD simulation, because to be honest, that was really, to me, I learned a lot about the dipole antenna, about what it's used, and as far as like how is it able to be reflective as far as the design parameters, as far as like beam width and gain and directivity, because those are really main important design parameters though here that any analyst can really calculate when it comes to advanced electromagnetics, or even in the field of a workforce, those are things that you would normally want to calculate or solve out as far as your design goes. Um, and also, this also brings up to my another point about how parameters such as permittivity and conductivity, how they're essential to here and how they're able to kind of help out specify what kind of source that you're really using, and as far as what kind of and also kind of broadens the idea about what is your design really going to be though here. So I figure that the permittivity and the conductivity, as far as like the parameters go here, they're very vital, and those are things right here that you really want to take though here, especially if you're trying to make it out in designing something. The hardest parts of the simulation, or the hardest part I would have to say, would have to be the complexity of the code for simulation 2. That one to me was a lot more tough because, like I mentioned, this one took a lot of coding though here. You can see it in my report, but this one took a really lot of coding, and it really took a lot of understanding as far as how this all fits, and the sheer complexity of it, about how much code had to be implemented. I know I cannot show it on here because otherwise it would have been a lot longer, but the fact of how long it was, and this fact about how much detail there had to be as far as like how a dielectric sphere works and about how each parameters work, it makes it that complex, and therefore it makes it a lot time consuming overall in general. Well, this concludes my presentation for the FDTD simulation. Thank you very much for all those viewers that are watching. Thank you so much for your time. Thank you.